let's talk about some spectroscopic properties and what this delta really means, as far as what we already know. And I'm going to talk first just simply about color. So I had last time that rack of test tubes with all the different color complexes in them. And those colors corresponded to an energy absorption, or, so we have white light in here, and when a complex absorbs a certain wavelength of light, you see a certain color. And we can use that sort of phenomenon to actually measure delta. So delta can be measured from absorbance spectra, or you can estimate it based on the color of the compound. So let's just remember what absorbance spectra are. If you take an absorbance spectra, what you do is you take a sample, which is transparent, and you pass light through it, and basically you measure which wavelengths of light are absorbed. So you would have absorbance on the y-axis and the wavelengths, usually in nanometers, and that's how our instruments read it. Sometimes you can also have wave numbers, which are in centimeters to the -1. So you will sometimes see wave numbers on the x-axis. All of our instruments have wavelength in nanometers, and the range where we usually look is somewhere between 250 and 800 nanometers. We can really only see to about 400 nanometers. So everything down here is UV. So this is the UV region, and then the visible region is up closer to the higher ends. So if I have an absorbance spectra that, let's say, it absorbs at 400 or let's say 500 nanometers, that's going to be my lambda max. So that's going to be your lambda max, or in other words, the wavelength of maximum absorbance. So if I drew a spectrum, this is what it might look like. And this is telling me that whatever compound I have, or whatever solution I have, is absorbing wavelengths at around 500 nanometers. And this can tell me something about concentration if I use the Beer-Lambert law. So Beer-Lambert tells me about concentration, or you can also use it to find something called the extinction coefficient. So you should know this from Gen Chem. Absorbance is equal to the extinction coefficient times B, which is the path length of the cuvette usually, times the concentration in solution. So there's a direct relationship between absorbance and concentration. So the more concentrated my sample is, the higher the absorbance would be. And then there's a relationship between the wavelength and energy, and that energy is going to tell me what my delta is. So the energy is equal to hb, which is the frequency, or you could write it as hc over lambda. So h is Planck's constant, c is the speed of light, the lambda is the wavelength, so it can also be written as hc wave number. Remember, wave numbers are in centimeters to the -1. hc over lambda, or hc times the wave number. And the wave number is just 1 over lambda. And the important thing to realize is that this energy is the delta. So the energy of absorbance is the energy difference in your orbitals where your electrons are being excited. So if I have, for example, a titanium 3+ compound, this is a D1 metal complex. Let's say I have an octahedral complex. I'm going to say that this is titanium hexaaqua. If I have a solution of this and I'm standing and looking at it, you can think of this little cartoon where there's a little girl over here looking at this solution, or you can think of this as the detector in your UV vis. If you have white light coming from something like the sun and going into this solution, the molecules in the solution are going to absorb some of this light, and it's going to promote an electron from the lowest energy ground state up into the next orbital, or from the HOMO to the LUMO. So if I take light and I zap this electron, it's going to bump it up to an excited state. And the difference in energy here is delta again, and so it takes that much energy to promote that electron. And so when you absorb light, in this particular complex, the wavelength of light that is absorbed is 493 nanometers. And that is blue light. But when I look at it, so if I was a detector, I would just see that 493 nanometers is absorbed. But if I have eyeballs and they detect color, I will see orange. If I tell you what color a compound is, you should be able to tell me about where in the visible spectrum the compound is absorbing light. And there's a cheater way to do this. Remember Roy G. Biv? I'm sure you guys have learned this in physics. Red, orange, yellow, green, blue, indigo, violet, just kind of together. So the wavelengths are, red is 7, depending on which source you look at, they have a little bit of a different range, but I'm going to tell you that red is around 700 to 620 nanometers. Orange is about 620 to 580 nanometers. Yellow is about 580 to 560. Green is 560 to 490. Blue is 490 to 430. And indigo violet is 430 to 380. And 380 nanometers is really around the range where we can't see color anymore. If I told you that I had an orange solution, you can look at this color wheel and say, okay, orange, well, it must be absorbing blue light. Because whatever the wavelength is, so if it's absorbing around 493 nanometers, you know that that's blue light, and you can look across to the complementary color and see that you would actually see orange. Because the light that's coming to your eye is basically white light minus 493 nanometers, and so you will see orange. We can use this information, so you can use color or you can use the absorbance maximum to calculate the delta or the energy difference between the lower energy orbitals and the higher energy orbitals. And in this case, if I knew I had a D1 octahedral complex, I have an EG and a T2G and EG set, you could have predicted that there was only going to be one transition here. So you might predict EG to the EG from the T2G. So that's the excitation. And see that there's only really one excitation that we would expect here from the T2G set to the EG set. So let's look at another example. And I'm going to use hexamine chromium 3. How many d electrons are in chromium 3 plus? Good, 3 electrons. So this is a D3 case. So we have 3 electrons here. Now if I excite it with light, I will get an excited state where one of my electrons has been promoted to the EG set. So how many electronic transitions would you expect for octahedral D3? How many types of transitions? Anybody have a guess? Huh? 3? 3 or 2? Okay. Where are you getting that from? Okay. It was actually a trick question. But I like the way you're thinking. So most people would say, remember this is T2G and this is EG. Most people would say that there would be one transition expected. And it would be from the T2G to the EG, just as I've drawn above. So you can promote electrons from the T2G to the EG set. And if you were asked to predict the number of transitions, basically you just, to predict it, or how many you would expect based on electron configuration, there's only so much you can do. And this is basically the only thing you can do. You can say, okay, well, I have electrons in T2G, and so they can be promoted to EG. That would be one transition. If the geometry was different, maybe you could have a different number of transitions based on how many higher energy orbitals you've had. But it's only an estimation. if I look at what you would expect, so let's say I expected one transition here, or even two, like Haley said, and I had some lambda max. This is absorbance over here. The actual spectrum, I know this is just a cartoon, but I'm going to try to draw it, looks like this. There are actually 4 different absorbances, which correspond to 4 different transitions. What the heck? Where are those 4 transitions coming from? So let's look again at the electron configuration of this D3 complex. I'm going to put 3 electrons in the bottom here. And now I'm going to actually label. I'm going to label my d orbitals. So this is going to be my x, y, x, z, and y, z in the T2G set. And then I have a z squared and an x squared minus y squared in the EG set. So if I shine light on this molecule, I could promote this xy electron up to z squared or x squared minus y squared. I could promote this electron up there. And it turns out that even though, so what I just drew is actually 2 different things. Promoting an electron from the xy to z squared is actually different than promoting it from xz to z squared. So this is what I drew in green. And this is what I drew in orange. And the reason that this is the case is because electron repulsions between electrons in different orbitals are different, or they're not equivalent because of symmetry. So when you have, let's say, z squared full and then x, z, and y, z are squared, they're going to have different relationships than when you have z squared and you have x, y, and y, z full. So what I just said was, so we're back to our old friend symmetry. And now, in order to predict or interpret absorbance spectra, we have to consider something called microstates.